this session. Thank you guys joining us. This is the collaboration sessions for the HTC24. Next slide. A brief introduction on the collaboration support services, just as a primer of what we're listening in today. There are about 20 active collaborations on the OSG right now, with 7 more that we are actively engaged and possibly on board in the near future. In a nutshell, services, collaborations, and the spectrum of service, of course, is very wide. We rely heavily on other teams to definitely on the technical part and all of these things, but we get our hands dirty with user support, data and software management, and cyber infrastructure integration. Collaborations leverage compute and storage capacity on their own, institutional collective, and on path managed infrastructure, such as the OS pool, OSDF, and everything else. Next slide. This is preliminary results. I was looking to find out, I've been doing these path reports for the NSF for the longest time. And one of the things that struck me is kind of like to collect some information of how the different pools kind of like stack against each other. As I mentioned before, a pool is basically an aggregation of resources, and we know one of them called the OS pool. But as I mentioned in the previous slide, each collaboration maintains their own pool of access to resources, and they can run a job there, or they can always flock, as we call it technically, to the OS pool. So they can use both of these two pools. So I just basically started looking at data a couple of days ago. This is just a preliminary as I'm trying to understand them. And as you can see, these are the cumulative number of jobs, CPU hours, and GPU hours. So being cumulative graph, what you should be looking for is the slope. As you can see, the slope indicates that it's pretty constant across the last 12 months. The thing, of course, that stands out is that we have a distinction between the total number or whatever you're looking at between the OS pool and their own pools, with their own pools still dominating. But there is definitely a significant usage of the OS pool resources. The only thing that kind of stands out in terms of growth is the red line for the GPU hours that you can see on this graph over there. There is an upward trend. That means that there is an acceleration in the usage of GPU resources for the collaborations that use their own pool. Now, I use collaborations in plural, and it is plural, but for this graph, effectively just think there is actually 2 collaborations that dominated. That basically effectively define it. It's the LIGO and the IceCube guys. So for LIGO and IceCube, when you stack them together, you see a little break happening about 7 months ago. The exact reason behind this is not understood at this point. We will be digging into that to see what basically accelerated the usage of GPU resources. So we're going to start the session. The session schedule is as follows. We're going to have a presentation from the Electromagnetic Collider group, and specifically EPIC. Sakib Rahman from Brookhaven National Lab, who was also yesterday at the panel, will present. Our own Brian Wackerman will give us an update on the token transition. Gluex from Richard Jones at the University of Connecticut. Nora Sherman from the Dark Energy Survey Group. And finally, we're going to close with a RedTop update from Vito. But the one who's going to present the results, the update, is going to be one of the PIs, Corrado Gatto, and he's going to join us remotely. So the first one in line is Sakib.
There's a clicker. Forwards, backwards.
Forwards and backwards. Okay, cool. Yeah, let's just go here.
Okay. Does the laser work?
It's not working. No, that's fine. All right. Hello, everyone. My name is Sakib Rahman. I'm a postdoctoral research associate at Brookhaven National Lab, working with the Nuclear and Particle Physics Software Group. And today I'm here to talk on behalf of the EPIC Collaboration Simulation Production Working Group And I'll be talking about the simulation campaigns that we run as an experiment, and just our experience on using OSG resources so far, and maybe a couple of use cases that come in down the line. So just to reintroduce EPIC, if you attended the group discussion yesterday, you sort of heard some of this before. But again, EPIC is the first experiment to be realized at the Future Electron Ion Collider in partnership of the two host labs, Jefferson Lab and Brookhaven National Laboratory. And we're an international collaboration with 173 institutions worldwide that are working together to provide insight into nucleon and nucleus down to the scale of seq quarks and gluons, leveraging the very unique and versatile EIC beam spec. So it's a very high polarized, high luminosity configuration that you don't have in other colliders. The OSG infrastructure is used to run large-scale monthly simulation production campaigns at the moment. We're at about 1 million core hours, but it's growing every month as we have more requests for different physics data sets that come in from our physics working groups. And this forms the basis of our detector and physics studies in preparation of the technical design report, which is very important for us as a project. And we're also using this opportunity to sort of develop distributed computing capabilities in advance of the operations phase. I'm not going to be able to show the video because I think it's just a cool animation of the electron and proton colliding. You can see the tracks, but moving on from that. Is it working? All right, just a second. Okay, find it there. All right, so just a little bit about our detector. So it's a multi-purpose detector that's designed to measure all the final state particles of interest with full acceptance and high resolution. And it's uniquely designed for the symmetric beam energy. So usually in collider experiments, you have a more symmetric configuration. That's not the case with, in particular with EPIC. But we have a range of different detector technologies. So we have the high precision silicon detectors that are arranged in sort of barrel and end cap configuration to track the particle trajectories that come out of the collisions in a 1.7 Tesla magnetic field. There are electromagnetic and hadronic polarimeters that are used for particle energy and jet measurements. There's a whole set of detectors that are dedicated to particle identification. So whatever's coming out, we want to be able to ID those. And this is just in the central detector. We also have sort of detector systems integrated into the beamline in the far forward and the far backward region that really allows us to measure particles that are close to the beamline. So this gives in together, we have wide kinematic coverage that's provided by the central detector in sort of collaboration with the far forward and the far backward regions. So that's our detector. And what are we trying to do with the simulation campaigns? So we want to be able to continuously deploy the software that we're using for the detector and physics studies, improve it every month, have fast turnaround. We want to be able to update those production outputs pretty regularly, because every month people are coming with like new physics and background processes that they want to study, making improvements to the detector design or the readout systems, and then also testing and developing our algorithms that we have in our software. And we also want to be able to validate and quality control for the simulation production on data sets that really require significant time and resources, which we don't have in sort of other places where we can run these simulation campaigns. Now, some of the data this is just some of the data sets and Monte Carlo generators in production. And like as you can see here, there's like different groups, and they're really looking at like a wide range of different sort of physics, and they're using different Monte Carlo generators. And what we've tried to do is sort of have a version control in place so that we know exactly what we're running. And then this list keeps growing. So being able to run these campaigns in an organized manner means that we need to have sort of a strategy that we follow every month. So every month, beginning of the first week of the month, we use for verification and validation. And then the second week is sort of used for targeted development. And in between those weeks is where we have our sort of tagged, what we call trained releases. So whatever the software status is at that point of time, the train leaves the station. And if you have more changes afterwards, you gotta wait for the next one. Sometimes people can't wait for the next one. They have really something specific that they wanna study or understand. For that, we have like the charters or taxis that they can request, but it's only done in very specific cases, urgent cases, and it gets filtered through our software coordinators who sort of decide the priority. But the goal that we have is to have everyone sort of unified into sort of these production campaigns so that we don't sort of redo the work that multiple groups can use. All right, so why choose throughput computing and OSG? I sort of mentioned before, currently the data sets in production are consuming 1 million core hours per month, but this is growing every month. People will come back and say that I need more statistics. I need 10 million events instead of 1 million. And then, you know, that's translates to longer runtime. So apart from that, why did we choose OSG? So having like a common interface template, like we can use the sort of HD Condor submit template without the need to adapt it to like specific sites. That's really helpful for us. Parallelism and ease of scaling, being able to run up to 10K jobs. So right now, like the highest ceiling that we've reached is sort of simultaneously run 10,000 jobs. So that's what I've listed there. But hopefully in the future, we can scale farther up from that. Ease of access management. So we have collaborators from like a lot of different institutions, and we're able to sort of facilitate everyone to use the resources. They can authenticate to CL logon, and it's sort of a common entry point without having to deal with individual accounts on separate systems. And then I would like to mention that one thing that I found really useful is that the support system is excellent. Like we have weekly meetings with OSG PAP, and then the ticketing system. There's a user base that's pretty broad, and I really coming to this meeting, I was encouraged by how many different types of users there was, and there's always something to learn from different people. All right, so leveraging the resources that we have. Like, are we just like running these campaigns and then never looking at the output? No, this is actually being used in our physics studies. So I just mentioned a couple of examples. So one is a group looking at electron-proton deeply virtual content scattering. And I'm not going to explain what the exact physics is, but it's relevant for imaging, 3D imaging the nucleons, so the protons and neutrons. And this helps us to understand the origin of mass and spin for protons and neutrons, just in simple terms. And for this, the electron identification is crucial. The detectors in the far forward region are crucial. So how is the simulation campaigns helping us? So if you look at the top left plot there, so that's just that's the generated particles in our Monte Carlo simulation. And then we have the reconstruction software that tries to reconstruct the sort of what we call the pseudo rapidity. You can think of it as a sort of measure of the scattering angle coming out of the collision. But if you look at our tagged productions, there's 24.04.0, that's the April production, and then there's 24.06.0, that's the June production. And the person looking at the April production sees that one of the detector outputs is missing from that plot. So immediately we know something's wrong, go fix the configuration, and we are back in business the next month. So it's really useful for us to have this fast turnaround where we can evaluate the performance of our detector in physics and also promptly identify any software issues that happen in one campaign, and then we can change it and have it corrected in the next one. Same with here, I just put another example here. This is looking at elastic electron proton scattering. So EIC will be the place where is the highest Q-square measurement for the elastic EP scattering, and is the first time it's being measured at a high energy collider. And we can look at, you can evaluate different reconstruction methods within the same campaign. So if you have multiple different algorithms, we can all evaluate it within the same campaign. And again, you can see the sort of 3 different plots following 3 different methods. So it's really helping us do our physics analysis and also with our sort of ironing out the bugs in our software, basically. All right, moving on. So, so how is this sort of coming all together? So what sort of synergy we have between the different sort of identities that are contributing support or resources to this? So there's now 2 fully operational submit nodes maintained by the Jefferson Lab and OSG, where we can submit jobs from. And that's helpful in terms of like if there's issue in one place, we can just switch over to the other one. Right now, we can access resources from international institutions. So we started with Alliance Canada as sort of a test point, and that sort of works. And then the next step is to do that better, and then also integrate INFN, CNF that's there. I would say again, like the participation in the regular meetings with the OSG path and also the Subatomic Physics National Team Canada has been very helpful to sort of with the Alliance Canada integration in particular. There's a write accessible X2D server at Jefferson Lab, and there's a S3 storage at Brookhaven Lab that are being supported. Ultimately, we want to have X2D at both labs, but I'm just mentioning what we have currently. And then there's a production.
The S3 storage in Brookhaven is coming late.
Yeah. And we have a production Ruchio server in the process of being deployed at Jefferson Lab. So since last sort of May 2023, we've had about 14 million core hours of simulation run and about 300 terabytes of output. I sort of listed the sort of top 5 contributing sites, and you can see there's a lot of diversity there. What we'd like to see is have more contribution from some of our allocated resources. So that's something that there is room for improvement there. Okay, so the current production workflow. How am I doing for time?
You're fine.
All right. So current production workflow. So we don't really have a fancy sort of workload management system. It's very lightweight. So we have the container currently being deployed. So it's a tag container being deployed to CVMFS nightly, but we have monthly releases, as I said, like the trains correspond to the monthly releases. And then we calculate the timing data in CSV files for each of the physics data set that we have. There's a HD Condor submit script template that gets modified based on what configuration we're running, the timing info, credentials, things like that. And then there's like a couple of shell scripts that build the submit script from the template each time for each data set real time during submission. And then post submit, that's what I was talking about yesterday. We have our input data sets in HepMC3 root format. That's in the JLab X2D, and that gets streamed over. We run the simulation workflow on the OSG resources. And then the output currently gets written back to S3 storage at BNL, and then we have a cron job that syncs the BNL S3 with JLab X2D. So as I pointed out before, you want to move away from that, find a way to directly write to the Jefferson Lab server, and that will come through the OSGF integration. So, all right.
Yeah, but 1 minute.
Yeah. All right. So, so this is sort of, I just put the template that we currently have. So that's the sort of call that we put on the submit node. It executes that shell script that takes in a bunch of parameters and environment variables. And then on the job node, it's just a simple run.sh shell script, which is integrated into our sort of tagged container on CVMFS. The submit script itself there's not a lot in it. It looks like just any other submit script that you've probably seen different groups show the last couple of days. The only requirement we have is probably like having Singularity so that we can access our container and run the software from there. All right, so lessons learned. Redundancy is helpful. There's been time where we've had issues related to low throughput on one submit node or another, and we could track it down through doing comparative testing. Monitoring and profiling of the outputs was essential to track down memory leak. We had this one, and I put the example here. We can see in our reconstruction software, the memory was just going up, creeping up over time. And then we identified the bug and fixed it, and now it's below 2 gigabytes or so for the entire duration that it runs. Monitoring the sort of connectivity issues from specific site was important since we stream input data over XRT. I don't know if we do it in a very efficient way, but still it's good to look out for that. Then also monitoring the destination storage if we're running into some disk or file system issues where we're trying to write it to. So that was helpful too. So again, redundancy, having sort of 2 different places that can write to was useful as well. So how can we improve what we're doing? So this is just a sort of a brainstorming slide. So the only concrete thing is probably the integration of Rucho into production. So the only remaining tasks on that are settling on sort of naming schema and access management by tokens. And then there's that the other point of integrating the storage sites with OSDF so that we don't have to worry about the token authentication and auto renewals, all that stuff that's happening in the background. And then the question that we have is like, how much more complex do you want to get? Do you want to switch to a workload management system instead of this sort of lightweight tool that we have right now? Right now, our Monte Carlo event generation is separate from the simulation aspect. You want to combine those, run our event generation on the fly, then we don't have to sort of stream it over the file system. But again, that would require us to have really good control over the generators and data sets that we have. So that's pretty much everything to do with the current production workflow. In terms of future use cases, there's one project, 82E, and it's not really a sub project of EPIC because the scope is EPIC and also factors beyond that. It's a 2-year project supported by DOE Nuclear Physics, and BNL and PPS has the lead on that. And they're trying to use multi-objective Bayesian optimization for detector design, taking into account detector performance, physics performance, and cost, and sort of develop the right monitoring tools and dashboards for different metrics. And part of that is using Panda's AI/ML services to support this workflow. And they want to be able to integrate this with OSG. And I think there was a request for sort of support on that recently.
Yeah, that's not gonna go far with Panda, but the rest of them, it's already actually on the access point, Tadashi and the other guy. So we'll see what comes out of that.
Yeah, and then the other one was like, we also have ML models that we run in our CI/CD pipeline, and we want to be able to do this in a easier way. So right now we're using SnakeMake. I don't know if it's the best choice if you want to interface with OSG, but I put it up there anyways.
Great
Right,
ideas.
thanks.
Thank you so much. Will you entertain 1 or 2 questions? Go ahead. I know that you want to.
Just to go on the snake making, from the HTC team, Justin Heemstra is working on improving the snake make executor, so it runs in OS pool type environments. Currently, snake make has a Condor plugin, but it assumes a shared file system.
Yeah, that's why I was like,
But there's at least working code. The upstream for the Condor plugin is a grad student who appears to have graduated, and we're having a hard time upstreaming the improvements, but we actually have Dagman will probably integrate better, but if what you have is SnakeMake, we can at least, help get that off the ground.
Yeah, the reason why I put up SnakeMake on there is because like right now we have our sort of physics benchmarks that run as part of our CI/CD pipeline, and that's in SnakeMake.
Yeah,
So it's easier to just take that and be like, okay, run it as part of.
What I don't understand is why Panda?
Well, that's what I said. It's like if you have better suggestions, we're
You just call going to Panda an upgrade, and that doesn't go in mind. Any other questions? Go ahead.
Yeah, I apologize if you said this and I missed it, but I think you made reference to, either an EIC or an Epic pool.
right.
Yes,
Yes?
yes.
But I also see a lot, I mean, like, I was just double checking to make sure my memory wasn't failing me, but I see Epic jobs showing up, or the project showing up on our daily OS pool reports too, so,
They submit to both, they can block.
okay.
Yeah.
Oh, so
On both access point, they
it's
can
just
block.
straight up flocking, so it's not that you're distinguishing workloads or.
Yeah, but the thing with the Compute Canada allocation is it's only accessible currently through the
Yeah.
Epic pool.
Right.
It's not.
They
yeah.
go through to the OS pool from our access point, the 23.
Uh-huh.
There goes OS pool, the JLab access pool goes to the Epic pool and blocks to the OS pool. So they go to all the OS pool to do different channels.
How much data do you generate?
How much data
How
we
much data?
So that's what I was sort of pointing out, it's kind of dynamic, like so far, out of all the campaigns that we've run since like last May, there's about 300 terabytes. But each campaign it sort of grows, because like if people ask for more statistics, then we just immediately have more data this campaign than the last one.
You're maxed out an hour.
Yeah, yeah. So
When you
yeah.
move to OSTF, I mean, how many objects?
Good
Yeah,
question,
yeah.
but we don't recall this from memory. As I said, right now they have 75 terabytes on OSTF, on our OSTF. And they have 300 or 400 terabytes on the origin they had at JLab.
Yeah.
Typically, I would say you divide this by the typical size of the output is like what, 5-10 gigabytes?
Right, so we're also like, right now, we're working on sort of a storage management policy to figure out, like, do you want to keep all the campaign data and how we store it, so that's still in discussion.
That's when Russia is gonna come in,
Yeah.
because you can leverage storage at the European sites.
Yeah.
All right, thank you again, Sakib, let's move to the line.
All right, so,
I don't know if the laser pointer is working.
yeah, never quite sure who come up in the rooms for these sorts of things, so I have a fair amount of details I'm gonna skip through and go around and see what the folks think is interesting, because that will leave more time for the science presentations, which the pieces I really enjoy. So a little bit about the ongoing upgrades, changes, transitions within the authorization ecosystem for us. So this slide is the short version of what we're doing. So historically, within all the different services we run, the authorization was identity centric. You had some sort of identity. You presented the identity to a remote service, and based on your identity, that service made some decision. You can write or not. You can submit a job or not. You can delete this file or not. So everything was really based on who you are. That's a problem. Because especially when we go out into the distributed system, we have to give you a way to have jobs act on your behalf. So maybe I used the wrong image here. I should have used a passport, but the power of attorney. So you were sending your power of attorney out to every single core on every single little place across the planet. And you know, if you're doing this big international collaboration, your power of attorney is in Pakistan, it's in Switzerland, it's in China. Pick your favorite country you don't like, and your power of attorney is there. not the greatest system, but it's the system that we definitely inherited from our forefathers. For the distributed system, we're trying to move to the right side of the stick. We're moving towards what we're calling capability-based optimization. We're moving to where the credential that we send around and the distributed systems look at are based on some sort of signed assertion. So here I use the baseball ticket, and it says that you are allowed to sit in row 15, seat 20. Doesn't say you're allowed to do whatever the heck Brian Bachman does. It says whoever holds this ticket can do this one thing. It doesn't say who holds the ticket. It doesn't say, you have power over everything, but just a single sign. So we're working going from this identity mapping system to a capability. That's, I could probably even stop there, just say that's the top, but a couple more details. The old system, the way we implemented these credentials, the identities is through X509. And plus a bunch of extensions that it turns out nobody else on the planet picked up besides the tech community. So as time went on, the number of users of this went down. The cost for the HEP community, therefore, to maintain the software kept going up, and eventually the primary implementation, the reference implementation, I guess you could say, of the software said we're no longer going to maintain this toolkit, somebody else has to do it. So those are all the things that we're moving away from. In the new ecosystem, the credentials we're using are called JWPs, which are currently what is used for a wide variety of tokens or credentials across the web. So this is probably the most common format, and using these has allowed us to, instead of use really highly technical libraries, allows us to use common libraries that other people offer. Like basically, if you're a language that interacts with the web, you have a library that supports these data. But again, those are the mechanism. The philosophy is an important part of what we change. We're thinking about, you show your capability at the door, and this happens to be the capability stuff. So even though we call these the token transition, it really is about moving to a different idea and philosophy behind how we interact with services. So a little bit on where we are. Actually, I did want to take one detour. One thing that we are in transitions, not only the client side, which I just showed, we also are on the server side. So the quote unquote grid community back in the day went off and made their own network of CAs, and these CAs are used for all post authentication. And it, well, I guess I could speak for myself. I could say the value add of these CAs for identifying hosts was about zero. And each one of these costs about $250,000 a year, less we did to operate. And so they're expensive. They don't add a lot on the value on the host side, particularly if you think the fact that we somehow think that we do a better job than the people that secure things. Like I always thought it was a silly sentence. So OSHA about 2018, 6 years ago, said, you know what? If it's good enough for a bank, it's good enough to protect our open science resources. We started using the CAD, the browser, the standard set of browser CAs, the same sort of CAs that Windows and Linux ship with. And nothing bad has happened. It's worked out, and it's saved us a lot of effort that we were able to apply and make other things. WLCG still mandates that. I have lots of opinions of why that is. I'm not going to say over a recorded session, but for some of these collaborations, this is still a sticking point that eventually the rest of the world will catch up with this. On the client side, going back to the tokens, we sometimes talk about this as if this is new, but actually, even tracing back further, we proposed the idea of doing capability-based authorization in 2017. We actually got some support from this, through the CC program, or CICI program. And it happened to be the same year that Globus decided that they were going to retire the Globus toolkit. So there was some fortuitous timing that those two went together. And it turns out our first big release where all the services, or at least all the major services, supported either authentication mechanism was actually in 2021. So this is now old enough that we're retiring the support for the first generation first approaches. So that was OSG through 6. And as I say, just because we add support to the new system doesn't mean that everybody rushes over and switches to the new system. And so we added tooling, we've made things better, but we're still got some work left to do to get some of these collaborations moved on and transition. If you are creating tokens and using tokens, one of the most important questions or things you need to do is decide on what software are you going to use for your token issuer. This is maybe one of the interesting aspects of this transition. Before we use certificates, and we used bombs to manage agreements. There was only one piece of software in the world that implemented this. So guess what piece of software you would use? It turns out with tokens, these are industry standard. There's a lot of options. So there's actually 3 different ones in use now. One's a very simple one where you just sign the token directly using the private key. No complex flows required. It works great for small organizations that don't have lots of distributed services. There's a second one, OA4MP, that is brought to us by the same team that does CI Logon. This is used by Fermilab, JLab, CHTC, LIGO, and probably about a couple others. The really nice thing about this one is it doesn't own your group user management, but really just does the token. It's meant to integrate into your existing system as opposed to replace the system. IAM is used in Europe by WLCG, and this is more of a full stack type approach. It has a web interface, it does the user management, does group management, it kind of does everything in one box. And most notably, it's the only one that can issue bombs extensions, which I think is one of the big attractions for WLCG.
You mentioned another approach in Europe. A few months ago that you were looking at to replace bombs.
So the EGI check-in team,
Yeah, the
which
check-in.
is based on co-manage, is discussing implementing bombs extension to replace bombs admin.
But it doesn't, it's
which-
not a token issuer itself.
They also have a token issuer on that, but depending on time, I might skip
Sure.
over the EGI check-in, but there's some other further differences there. Flying through some things, OS pool, things where Pat runs it end to end. The transition is done. Right, basically all our services are cut over because we control and can push and evolve a lot of the software. LIGO works incredibly closely with Pat, and they're really set up well and are there. I think if they weren't in the middle of a science run, they'd be able to kick out the legs of X509 and just tell their users to move forward. They've asked us to keep things around until the end of their science run to be conservative and avoid disrupting their workflows. And this is just part of doing business in a production system. Sometimes you have to keep things around because you want the science to keep going. One really interesting thing that I love is at the end of LIGO 04, say Logon plans to shut down the CA. So CI Logon has been issuing user certificates for probably a decade and a half or so. As far as I know, they're the first CA to shut down because they say no one needs it, as opposed to all the other CAs that shut down because they ran out of money. But I think this is a huge success to say, you know, mission accomplished. We've retired the thing as opposed to no one will give us any money anymore to keep on doing the same thing over and over. JLab, one thing I mentioned, you have some insights. This is one that they use CI logon, they use something called Vault, these are online, they're integrated. Either they don't complain a lot, and they're suffering in silence, or things, they're mostly working.
Yeah,
right?
mostly working.
Right, so yes, we've seen pain points, for both JLab, Fermilab, the boundary layer between Condor and Vault has been a common irritation. But JLab's been, working well. Fermilab has a lot of similar technology set up as JLab, and they still have quite a bit left to do, because they have a longer legacy of working with services and just a lot of old things left to come over. That said, they use CI login for user certificates, so at least right now, they have a less than 12 months left because that is being run by the language vendor. WLCG is a huge topic in itself. CMS alone have access to their transition wiki page, and it's good 10, 20 pages long of all their internal service left to do. Important things is one, they've been really slow to cut over their token issuer production. Turns out their old system only worked on EL7. So at some point they said, oh crap, this loses support June 30th. I guess now we're going to cut over to the new system. So by hook or by crook, they made it over. And then the other thing that's really the big development project, the big missing chunk for everybody is FTS. So FTS, I'll show here, works with tokens, but this was done in a pre-release version, and they actually haven't gotten it out the door. So the core FTS guys are tired of my email saying, hey, can you make this an official release yet? So these are kind of in the almost there phase, but for me, I'm at least a little worried about the fact that they're still not.
You also got 12 months.
Yeah, so this particular graph shows for DC24, the big data challenge WLCG did. These are all the CMS average volumes per day. You'll see, so here they're doing 100 gigabytes. Apologies to the network people, I did put a graph in bytes a second. So you can see they peaked at 100 gigabytes a second. And by volume, about half of this was completely token based. So short versions, it works. This can be there. We're just waiting on the FTS team to mark it off as production and give it the official release. So we're so close we can taste it, and we're so close it's frustrating.
I have 1 minute.
Yeah, in 1 minute, there are other people's working on tokens. People hear lots of stuff about other token profiles. EGI, AR also has a token profile. An important thing, since these are key value pairs, you can implement any model basically in key value pair. You can go back and re-implement GSI using tokens if you really wanted to. So people ask me, or what these people are doing compatible with what we're doing. And I always tell them, very unsatisfying. At the profile layer, we can translate these back and forth. The hard question is, are these authorization models compatible? So there's a work group trying to mesh these things. It looks like the profile, the keys, and the schemas could be compatible, but what's convinced at are these authorization models would be an interesting aspect. So, conclusions. The token transition is no longer a single progress bar going to 100% completion, because we're at the point where the common pieces are done, and now it's a bit collaboration by collaboration. How many services do we have left to go over? So maybe it's a dozen progress bars on depending on who it is. It's a little bit uneven for things that really are completely within the control path, or we can help them with all the pieces. It's largely done. Particularly, I think Fermilab and JLab have benefited immensely from their CI logon partnership. And for WLCG, because A, they have to work a lot with the European side, and B, they just have this huge number of services. This is something that's gonna be ongoing.
Thank you, Brian. Any questions for Brian? Go ahead.
Yeah, Brian, I'm a little confused. Why is tokenizing MTS your problem?
Oh, it's not. It was my problem, it'd be done. The problem is, this is an external piece of software developed at CERN. So there's only so much I can do to, job over them to finish up the project. We're good individuals, but we've had a hard time even contributing functionality to the software from the outside to move it forward. So this is a place where it's very much an externality that we don't have a lot of control. The piece of which they're good collaborators, so we're not gonna, I don't think anybody's talking about taking them to further anytime soon, but it would be nice to have a better way to inject, hey, this is a real priority.
But the priority does come from the WLCG actually, right? Because both Atlas and CMS are heavy Russia users, but Russia depends on MTS, so if they're going to move to tokens, the pressure is right next door to them.
Yeah, well, I'm just an impatient person. I would want to do nothing.
Lots, you have a question?
Yeah, for the token on the OSP, especially REP. You don't want to trade for jobs, but it is tricky to get tokens to users to upgrade. For example, outside.
Yeah.
Have any,
Yeah, so actually, it's not something I've shown much on the facilitation team, but the Pelican client now has the token acquisition built in. So the same device flow that you do for SSHing in. So that's built into the Pelican client now. So if you are sitting from the outside world, not in Congo, not at AP, and you want to copy something and it doesn't have the token, it will do that device code flow and just give you a browser link to approve. And then it also gets the refresh token. So for the next 30 days, your laptop, terminal, whatever, can continue to upload. So if you have a full management. Yeah, so that's integrated with the APs that are co-managed. Yeah.
There is a plan with Vigo to do that. There is a plan with Vigo to do a Kingo thing, but we'll probably discuss later. Fabio did mention that, and they are in morning sessions. I was even confused because it seemed like it doesn't have the dependency of for your identity management to be on commands, but it does.
It depends on your identity management being on OAuth.
Yeah.
Device.
Right.
Right, so it just happens to be. That's true, Orchard Connect uses Globus, which. It's true that it might just be a matter of making sure that all the ducks. Don't think they'll be.
Let's move on. Thanks a lot, Brian. Again. Next one is Professor Richard Jones. Richard, can you hear me? Yes, great. You're sharing your screen and you have the mic.
Okay, testing my mic.
We can hear.
Okay, thank you. So I'm Richard Jones. I'm at the physics department at the University of Connecticut and a member of the GLUEX experiment. This is a intermediate energy nuclear physics experiment at Jefferson Lab. And I'll tell you a little bit about that in a moment, but just the general overview is I'm going to describe an opportunity to accelerate our scientific mission as a collaboration through the use of the resources, the open science grid for a new application. And then I'll describe the barriers that we've run into in trying to exploit that opportunity. And finally, some adaptations that are now making those barriers disappear that have been really enabled through the OSDF development. Okay, so let's start off then with an overview of the experiment. This is a typical intermediate energy experiment, which is sort of a one two story high experiment built into an accelerator complex. We have 9 GeV photons and a fixed target. And our scientific program is a mix of heavy quark and light quarks spectroscopy. We were commissioned with the 12 GeV beam upgrade at Jefferson Lab that came online in 2014. Our first physics run ended in 2019. Second run is just ending now. And right this week, there's a program advisory committee proposal for phase 3 that's now pending. Okay, and this would take us through 2029. So this is we're in sort of midlife right now with this experiment, and heavily trying to exploit opportunities that we have to analyze our data in a timely way and publish. So our standard way of using the Open Science Grid so far has been Monte Carlo simulation. We had this in the plan from right from the beginning, and so we have 10 years of experience in doing all of our Monte Carlo basically on the Open Science Grid, and it's been a very successful and pretty wrinkle-free experience. However, the lion's share of our compute is not in the simulation you see. 35 megacore hour per year is our simulation demand, but for our reconstruction, we need 4 times that per year. And in our phase 3, which I'll talk about in a minute, there'll be another factor or 2 or so in the experimental event reconstruction demand. Where are we getting those resources? Well, our original plan was to request the growth to happen in the JLab's own compute facility. It means that compute is next to where the data are, and it simplifies the delivery problem of data to compute. It turned out, though, that the demand for that compute facility far outstripped the resource growth, and so we were able to get time at NERSC, which is a national HPC platform, and that's where most of our event reconstruction is now happening. However, we've been faced with a limitation that we cannot get enough allocation to analyze our data in a timely way. And this is really the challenge, which I call the elastic computing resource challenge. Here is to illustrate that. This is our pattern of use at NERSC over the last 6 months. So you see, I've made this too small for you to read, so you just listen to me. At the beginning of this plot, it's January 1st of 2024, and in the middle of the plot is today. The right-hand plot of the plot is today. And the vertical scale is that is these funny NERSC units, which are not core hours, they're so-called node hours. So you have to kind of rescale it with me. But our total allocation for the year is 150, and this is 100. So this is more than half of our full year spread over 6 months. And that line there that you see drawn as a straight line is sort of what we would have to stay below in order to not outstrip our ability, not to overuse our allocation and run out before the end of the year. And so now I want to describe to you our bursty pattern of use. And it really follows the way that science is done. So this initial period was we were looking at the data and calibrating, and you recalibrate and recalibrate and recalibrate until you're happy with the first 1% of the data. And then once we're happy, we say go, and we produce or cook all of the data. And that I call the reconstruct phase. That's where we use all the compute. So you can see us starting well below the line, ending up well above the line. And we reconstruct that. You would like to shrink to as quick a period as possible because your physicists are waiting at that point. Then once we get those results back, then the graduate students and postdocs go back to work, and we're analyzing data. And the paper appears here. This is an actual timeline for an actual project that happened this year. However, these reconstructs only subtended 2 weeks of data. Okay, so this is that reconstruct period was actually data from 2 weeks taken in 2022 that had to be reconstructed because of poor calibrations during the first attempt. All right, so this sort of illustrates why when we have larger data samples than just 2 weeks, we're going to be outstripping our resources quickly. And that's where we need elastic capacity. So I want to illustrate the challenge of getting elastic capacity on HPC centers through this experience. Last November, we put in our request to NERSC. This was reported at our collaboration meeting in May. So I'm quoting from the slide from the person who wrote that proposal. Here's our request, 350K node hours. Here's our reward, less than half, 150 of them. And we've already used, as you saw, 50 node hours. So this is well under what we're going to need. In fact, we have data from 2023 that we haven't cooked yet, and we need 300K of these node hours, and we have no. This will take us 2 years at our present NERSC allocation just to get the data produced, and then analysis can begin. That's a 2-year delay in graduate student completing their degrees, et cetera. So what Alex writes here, you can read it yourself. He's comparing these two numbers. You can see here as I circle them, and then he writes, request more at NERSC, yes, but can we use other resources? And the OSG is highlighted here. This is the opportunity I want to describe. Looking down the road to GluX phase 3, starting in 2026 or so, we're going to have a beam intensity increase by a factor of 2. And so this is going to further intensify the pressure on production, that is event reconstruction compute. So that is my demonstrated, let me say 2 possibilities for elastic expansion. One is you either wait for 1 to 2 years to postpone your analysis until the cooking is done. And that's our present HPC operating plan, because we don't, that's what you have to do if you have no opportunities for other resources. But otherwise, we can exploit untapped capacity with HTC. I want to talk about that for the rest of this talk. Okay, so what stands in the way of us taking advantage? There are myths and realities. So let me first talk to you about myths. This particular myth is a well retold story. And it basically is like this: Monte Carlo simulation is appropriate for HTC. Event reconstruction needs HPC. And you might be surprised to hear that, but it's often retold. It's a GluX truth or a truism within GluX. Monte Carlo OSG, event reconstruction HPC. So you have to go to NERSC, you have to go to JLab's compute farm, where you can allocate whole nodes at a time and get quick access over an InfiniBand network between processes. Now, this doesn't mean that it's actually an HPC problem. It means that there's this myth that we need HPC to do event reconstruction. I'm going to tell you why. However, from a purist point of view, event reconstruction is inherently HTC. So if you were a computer scientist looking at this problem, you'd say, what is HPC about this problem? It isn't. However, there are HPC features of it that have grown in through our history. And let me talk to you, and these are the realities that contribute to that myth. Okay, a shared experience that really builds these myths and makes them kind of true in some way. Our recon framework. So this is the framework that contains applications and the workflow management. It was all developed for HPC on HPC, right? So experience in running these applications is all there on the HPC side. That's why it was so easy to move it to NERSC. And our workflows assume HPCs, because I'll talk about that in a minute. And so new effort is required then to recast these frameworks and workflows and adapt them for HTC. Okay. And along with that, one needs then better means to access real data. So adaptation and access. two topics that we'll cover for the rest of next 3-4 minutes. All right, so what does an HPC job look like? This is a particular snapshot of the Cori cluster at NERSC, and this is where we're running right now. So we have chunks of data that come in that are 20 gigabytes large. Those get read in by one node. This is a Haswell node on the Cori cluster, 32 cores. It runs for 8 hours, and it spits out a 5 gigabyte reconstructed output file called a REST file. Okay, that is basically what an HPC job looks like. What would that look like recast as an HTC job? You would want to slice up that input data sequence into at least 32 bits so that within the 8 hours, you could crunch them on one core and 4 gigabytes. However, it turns out that on the OSG, one would really like to have less than 8 hours. It's just easier to get time if you can do it in 3-hour, 4-hour slices. And so I'm going to describe it as basically a chunk, which is 1/70th, 1/80th, which is the way I actually run the feasibility study. So 300 megabyte input file, producing a 80 megabyte output file and running for 3 hours. So there it is, summarizing what I just said. Single core, and the IO rates are extremely low. Okay, so this is a detail slide. Maybe I'll stay here and I'll say what that slide says and flip through it because I don't want to get into technical details and get lost. Here, if you look at the left-hand side, this chunk of objects of input are coming in blocks, which are compressed blocks, and they have all the events, all the objects are scrambled within these event blocks into because they come rolling off of a streaming platform for the online,
Richard,
and they get yes.
I think our copy of the slide stopped updating because we're seeing slide 13, but I think they're talking about slide 14.
I went back because
He said he's
Okay,
gonna do
let-
documentary.
All right, sorry.
I can stay here. Let me just say that 20 gigabyte file is made out of little blocks. Each one of those is irreducibly compressed. But if I'm going to break this up, I can't send that 20 gigabyte file to 60 nodes. I've got to, on the fly, split it up. I've got to take the pre-run and the pre-start, which contain the qualifying metadata that I need to interpret these blocks. And then I chunk up some blocks out of the middle of the file, and then I put the terminator at the end. So this little chunk here is a slice out of this stream. You see and this is all accomplished on the client side over xrootd. So the way I did this for this feasibility study was instead of changing the xrootd protocol, I just basically rewrote the POSIX xrootd client library, and I read the data using the API, the standard xrootd API. I reassemble this object on the client side and I hand it to the applications. The application is binary unchanged from HPC, but I have this layer in my container that takes the data and chunks it up into a mini input. So this is the feasibility study. I took 35 terabytes, and it was going to be about half a mega core hour, and so it's a good sort of feasibility study. How well does this work? And here I am running. You can see the number of cores simultaneously crunching. Starts out on the Wednesday of this week, so you can see November 21st, and within say 12 hours, I'm up to 10K cores. I go up to 15K cores, and I'm done. So basically, the work runs out, and so I have to wait for all those jobs to finish, and we're done. So within that period of what it looks like 48 hours or 37, I think it was 38 hours, we're able to complete this 500K core hours. So there was some success there, and I don't want to get into details. This is how I chunked up those larger jobs to make them fit into HTC 4-hour, 1-core jobs. And there were 126 kilo jobs that ran during this short time period. And the fact that we could get all of these cores running and effectively use them, I thought was an achievement. But you see, it didn't happen at the first. At first, I had a real hard time trying to get good throughput. What difference happened on November 20th that changed from November 15th? And the answer to that was data access. Here I had no data flow orchestration, and here I turned it on. So it made a big difference. Okay. So what is data flow orchestration? It's a web app that I wrote called Traffic Advisor. It was just something ad hoc that I created for this test. And it's just a web app. So this is a web page that I just opened up and just took some slices from. So you can see here a visualization of what's happening on the network. The resource that's being accessed here is the Yukon stores XRootD server where the raw data was staged. And this is the Purdue OSG site that's reading the data. And the colors mean basically the green means successful completion. The purple, you can see here, means that when the client started up on the OSG node, it sends a request to the traffic advisor saying, here I am, I'm on this site, I want this resource, would you give me a permission? Basically, it's advice. Would you give me advice? And sometimes it says, wait, because there's too many people at Purdue trying to grab these data. Can you wait for 5 minutes? And that's the purple. And if it was given, once they were given permission and they started to flow, that's the green. And if it finishes successfully, it's colored green. If it's red, it's failed. And you can see that I'm getting a lot of waits. And so this button over here is basically, this is an interactive web interface. So if I click that maximum allocated bandwidth, you can see here, I'm limited at, if you go down to the bandwidth down here, I'm limited at 100 megabytes a second. You see the hair is being clipped. Then I clicked on this config limit right here, and I clicked on it and I typed in 500, and you can see it just jumped up to 500. And these basically just increased so that I'm not waiting anymore. However, sometimes you can turn it up and you basically kill the site. Why do you kill the site? Because TCP, once you hit a capacity, it dies. If you hit a bandwidth limit and you start retransmitting, TCP will just basically drop by a factor of 100 in its throughput overnight. So that's what happened here at this site. This is the Syracuse site. We had lots of nodes there, but the network was pipe was rather skinny, and you can see eventually, because I had so little success rate, I had to change my config limit to 1 kilobyte a second to prevent it from basically just wasting nodes there. They were never getting their data, or you can see a tiny little slice here of green. But with the ability, you can look at sites across as you're doing your production, or as I was doing my production, I could watch each site, I could tune its config. So it was like a smart grid where I was able to manage who's asking for what at what time. And by quenching this particular config limit, I would make it fail over from XRootD to the next option. So there were many protocols. This is also Syracuse reading from the same site, but now notice that the resource is going through the OSDF. This, if you're not familiar with CVMS, just think that's OSDF. Same file, same set of files, same origin, but through OSDF. And you can see Syracuse has no problem keeping up with those data. Okay, so this is kind of the lesson that I learned from it, that if you just turn loose onto opportunistic resources and say, call home, grab data, things do not work. And that's what I showed here, right? Do not work. But we're using proper orchestration, they did. And it was important to be awake and watching so that this is happening. All right, so I see that you're moving forward. Do I have 1 minute?
Yes, you do.
Okay. Was the myth dispelled? I would say yes and no. When I showed these results to our collaborators, they said, that looks like an expert-only system. who's going to actually sit there day and night and run that thing such that you have well adapted throughput. And I think we all agreed that that test was actually 2021. We are still not doing reconstruction. Why not? Because we think it awaits enhanced data access tools where the grid becomes more transparent and it doesn't require this kind of micro data flow management orchestration. Right, and this is our hope that the OSDF is becoming that this sort of self regulating system that supplies data effectively without a lot of friction. All right, and so this is our dream, okay, where we have tapes being staged on cache at JLab, and then a JLab OSDF origin that's delivering data to the OSG nodes. And we're ready for it when it arrives. I would say that here are the three things that the three specifics need to be checked. First, we need lab-wide release policies. Turned out that when I requested this from JLab, I was working with the folks at OSG, and the first question I got was, are you guys sure that you're allowed to release these data like that? And so we need to get agreement on what policies regulate access. Then we need to get our CI logon based token infrastructure working for GlueX and the new JLab OSDF origin set up. Okay, so the conclusions, GlueX is underserved right now by our HPC resource requests. We have demonstrated capability on the OSG, but we have data access barriers that prevent us from effectively using it. And we're on the verge of having an important acceleration in our science enabled by the OSDF plus OSG.
Thank you. Thank you. That was actually really good talk. Anybody has a question for Richard? What is about OSDF that was not present before? I mean, you deployed an OSDF, and then I think there was an OSDF at some point, right?
I think basically that somebody, when they set up the OSDF, the CVMFS, I would say when they set up CVMFS, they also thought enough about it to say, what kind of proxying are we going to have to put on our university boundary or border in order to not have frictionless access to data? Because if I didn't have that, I had ability to just from a worker node at Syracuse to do an outgoing connection, but there was only like 50 sockets. They probably had a NAT or something. I don't know what it was, but yeah, it was just a tiny tube. And the person who set up the CVMFS thought that through. That's I think the answer.
All right. Okay. There are no other questions. I would thank again Richard. You can stop sharing the slides.
Okay.
And is everybody here? Who's next? Nora. Nora, are you online?
Yes, I am. I can begin sharing now.
Excellent. Go ahead.
Alrighty. Hi everyone, and appreciate you guys encouraging remote participation. Today I'm gonna chat about hunting for the screams from the stellar graveyard, and I'm hoping to use this talk a little bit to focus more on the science rather than some of the resources that have been discussed now, because obviously what we're doing relies on these. That's why I'm here today. But it's kind of exciting to talk more, or to talk also about exactly what the science is that we're doing with this. So that's what I'd like to talk about today. And first, that begins with, oh dear, Zoom issues, of course. That begins with a reminder, or potentially, maybe this is new, that the universe is actually expanding right now. And it's not just expanding, it's growing at a faster and faster rate. And we typically attribute it due to the mysterious force known as dark energy. And if we really want to begin to understand what exactly dark energy is doing in our universe, what it is, one of the things that we can do is we can look at the Hubble constant, the current rate of expansion of our universe. And of course, lots of people have gone about doing this. So we can see, oh, I bet you can see my mouse. So we can see here are some of the experiments that have done it. But there is actually a large discrepancy present in H0 measurements between early versus late time measurements of the Hubble constant. So experiments like Planck that rely on cosmic microwave background data, so early time data, get values kind of close to this, while late time measurements like those that performed by the Shoes experiment, and I could tell you exactly what this acronym is, but really you just need to know they really forced that H not in there. They rely on supernova data, which is a late time measurement of the Hubble constant. And these two measurements differ by more than 5 sigma. You might be wondering to yourself, if you're not already really well acquainted with this problem, whether that 5 sigma actually translates to other experiment measurements. And yes, we see it across early versus late time measurements of the Hubble constant. So the experiment I work, this whole discrepancy is known as the Hubble tension problem. And the experiment that I work with, which is the Dark Energy Survey, has a subgroup known as the Dark Energy Survey Gravitational Wave Group. And what we're trying to do is we want to offer insight into the Hubble tension by performing a standard sirens measurement of it. And what that does is it combines both electromagnetic and gravitational wave data from a single source, which is the binary coalescence of dead star remnants. And those dead star remnants, of course, make up the graveyard I alluded to in my talk title. So it does seem, I think judging by a couple of the talks that I've heard that you guys are largely familiar with gravitational waves, but quick reminder, the ripples in space-time caused by accelerating objects. The LIGO-Virgo-Kagra collaboration can detect these. These are earthbound gravitational wave detectors. I've actually attempted to put pictures of each of the detectors up here, and I want to point out, for anyone who's not a gravitational wave scientist here, that we're currently in the 4th observing run of this collaboration of earthbound gravitational wave detectors. And we're kind of in a renaissance of data right now. The detectors have incredible sensitivity, and we approximately have 4 of them observing right now. So we can hear a lot of the screams from the stellar graveyard, which are the gravitational waves. We kind of think of that frequency, gravitational wave frequency, as if we if we boop it up a little bit to something that we can actually hear. Now, when we look at gravitational waves, they actually provide us with a distance to the binary coalescence event. And when we're measuring when we're doing a standard sirens measurement of the Hubble constant, we want that distance because it is one of the 2 things that we can measure in order to then determine H naught. So if we get a gravitational wave detection for an event, we can get the distance for it. So that leaves us with needing one more thing, and that is the event's redshift. So certain of these dead star remnant mergers will also produce a electromagnetic counterpart. So if we take, for instance, binary neutron star mergers, they produce an electromagnetic counterpart that has both a gamma ray burst and kilonova component. Now, this kilonova component is particularly interesting because it's able to be optically detected. So a kilonova occurs when the neutron-rich ejecta from the neutron star collision is heated by something known as R process, and there are really 2 types of kilonovae. There's the blue kilonova, which is heavy metal poor, and then there's red kilonovae. And they can last on timescales between days to weeks. And over here, this is actually the light curve of one of the first and currently only ever detected kilonova. And I'll talk a little bit more about that later. But if we find an optical counterpart to a gravitational wave event, we can connect it to a host galaxy and measure the redshift. And with both redshift and distance data, we got distance again from that gravitational wave signal, we can measure H naught. And if DesGW can measure H naught to a high enough precision, we can go ahead and figure out where is the error arising from in these other measurements that I showed before, potentially? Or just see, hey, does this measurement that is not reliant on the same systematics that went into the other two, does it align more or less with a one of those measurements? All right, so yeah, I mentioned that when we would talk about the first ever detected kilonova, and that was in association with the gravitational wave event 170817. So an event that occurred in 2017 on August 17th. So this was the counterpart to a binary neutron star merger. So two dead stars, which were neutron stars, collided. We picked up a gravitational wave, and then we were able to follow up on it. And so when I say multi-messenger follow-up, there were numerous experiment telescopes, instruments looking for this object in our sky. We were able to detect it across the electromagnetic wavelength, and DesGW was one of the teams that was able to discover this kilonova, and we actually performed an H-naught measurement on it. And as you can see over here, that H-naught measurement actually fell pretty much in between the two of the contentious measurements, but our uncertainty on it was far too large for it to be considered significant. So in order to actually perform an H-naught measurement that will give us that insight into the Hubble tension problem, we would need to detect far more kilonovae. So DesGW is an optical follow-up program, and in order to detect a kilonova, we rely on the instrument, the Dark Energy Camera. DCAM is located in Chile at the Cerro Tololo Inter-American Observatory, and it observes across these bands between 400 and 1065 nanometers, and those translate to GRIZY optical bands for the camera. And I did reuse this slide, I'm sorry, so this goofy person is me. I went to Chile last year and observed on this telescope, very exciting. But maybe you guys aren't so interested in the cool telescope side. So really, so one thing I should mention beforehand is DCAM is a quote old instrument, but it's incredible for what we do. It's not old, but it's kind of old. And it was originally used for the dark energy survey itself, which observed in this footprint here, which depending on how angry you are, looks either like a futuristic tank or a little bit like a hummingbird. Since then, DCAM has pretty much observed the entire southern sky, providing us with a huge image data set and quite a significant portion of the northern sky as well. But yeah, this is instrumentation stuff, but what actually are we doing, and what is the computing that we're doing in order to look for now the screams from the stellar graveyard? In order to put some emphasis on what exactly we're doing, I'm going to show you a more recent follow-up that DesGW performed. So there hasn't been a second detection of a kilonova, but we are still looking for one. So just to remind you, that first kilonova happened in 2017. It's now 2024. It's been a long time since we've seen anything, but we are trying to get way more detections in order to help resolve potentially the Hubble tension problem. So what exactly is DesGW doing in all of this? Well, we perform a elaborate follow-up on gravitational wave events. So LIGO will detect a gravitational wave event completely independent of us, and what it does is it releases a notification to the astronomy community to say, hey, something interesting happened out there, go ahead and take a look if you want. So over here in the right-hand side, we actually have an interpretation of a sky map that LIGO would have released for this event. It is S240413P. If you guys are starting to pick up on this, it happened in 2014 in April on the 13th. So this is what the event looked like. This is what we would consider a fairly well localized event. It was only 11 square degrees contained within this and this little contour here in our sky. And this is very well localized for the type of event it was. It was a binary black hole merger. So two black holes merging together. And it happened somewhere in this portion of the sky. And so when LVK releases the gravitational wave information, optical follow-up programs like DESGW will then try and image that area of the sky. And so DESGW in particular, we use DCAM to do that. So these funny little pink shapes up here represent the portions of the sky that DCAM imaged. And DESGW itself uses a pretty robust pipeline in order to process these images and get out useful data that we can then look at to a finer grain in order to figure out whether or not we identified the kilonova. And it's this pipeline that relies on the resources and variations that we've discussed today. And just to skim that over, it does image processing, which reveals the unique objects in our sky, and then we can apply a set of cuts. So if I go ahead and show you over here, essentially our pipeline has found in this teeny tiny little area of the sky 31,017 potential candidates. So things that have changed from when we looked a while ago to right now when the event happened. And these changes, this is what we're looking for in this type of search, because that could be an optical counterpart that was coincident with the gravitational wave event. So it could be something, it could be the actual counterpart to that gravitational wave event. But 31,017 candidates is an awful lot. So we know that some of those are actually products of our pipeline as well. So we need to begin applying useful cuts to bring our data down to stuff that we're actually interested in. So this includes machine learning score cuts on the physicality of the detection, whether or not the detection was time separated, and actually quality, i.e. did our pipeline actually mess up significantly while it was detecting this event, and if so, we can get rid of things like that. And then we can also apply cuts that indicate whether or not it actually occurred in the region of interest specified by LVK. And so just to make sure we're coming away from this slide with all the useful information we want here, this also down here represents the actual strategy that DESGW used in order to image this. So we observed for 3 nights. These are the specific bands. And if you guys are super into astronomy, some of these things actually talk about the sky conditions. I'll note before I move along, and I think I tried to make this a nice, short, sweet talk for you guys. I will note over here just this sensitivity plot that we use in order to hone our actual follow-up. So this was a binary black hole merger. Binary black hole mergers are actually not well predicted to, well, big asterisk on that. You can ask me about it. They're not well predicted to produce electromagnetic counterparts. So if a gravitational wave merger doesn't produce an electromagnetic counterpart, how exactly is it useful to DESGW when we said we want something to connect, we want something optical to connect to a host galaxy in order to get that redshift information? Well, it's useful to us because there are actually conditions under which binary black hole mergers could be optically bright. And so this plot over here is actually probing, showing how our observations could probe the parameter space in which a binary black hole like 13P would be optically bright. So that's what we can see here. It would need to fit in this tiny little portion of our parameter space in order for our observing plan to have detected it. So it's been a minute since I looked at this presentation. So yep, this this is the end here. So just to remind you, the universe is expanding and we're having difficulty determining at what rate exactly it's doing it. So DESGW uses a standard sirens measurement with both gravitational wave information provided by LIGO, Virgo, Kagra, and electromagnetic data that we collect using DCAM and then analyze using our search and discovery pipeline. And I shared a little bit of our resources. So with that, do you guys have any questions?
Thank you, Nora.